Welcome everyone who's just joined. Thanks for attending today. We've got an hour here to talk about AI noise reduction and deverberation. For those that don't know me, I'm Jason Spooner. I'm an applications engineer. I work at Biamp. I work for Biamp in the UK. I mostly deal with post-sales technical support. And I joined Biamp at the beginning of 2020, but I've been supporting Biamp products for quite a bit longer than that. And this is the agenda for today. So we're going to look at what's new, have a functional description of the technology, how to implement it, and other things like that. Some time at the end for questions. But before we go any further, I wanted to define what is noise. Today I'm going to talk about noise extensively, but I looked up what does it actually mean, and I found 3 examples which are from different fields actually, but all relate to our own field. And an obvious one to begin is a sound or sounds which are unwanted, unpleasant, or loud. That's pretty obvious that applies. And another one here is probably talking about system noise, maybe hiss from an amplifier, but any negative change in a signal that we don't want in an electronic device, and we're making electronic systems here. And this is probably from the scientific field, but unexpected information in a sample that is not useful and can be ignored. And the reason I'm bringing these definitions up is because we're actually looking at 2 concepts today. One of them is noise in the traditional sense, any component in an audio signal or in an acoustic environment which we actually don't want. It's extraneous to the thing we're trying to pick up and transmit. But also reverberation fits into these categories as well. And the technology we're discussing today deals with both of these concepts. So I'm going to use the term noise a lot, but noise in the traditional sense and reverberation can be considered in the same vein. So a quick run through of what's new. The big ticket item is the one on the right there. So we've added user configuration of this block in Tesira 4.7 onwards. But there are other things that are new as well, and I'll just briefly touch on those. So if you've been using Tesira or Devio SCX with Biamp launch since version 4.5, you'll know that we have AI processing in there already. But in 4.7, this is very much a new next generation AI process. So it's an all new algorithm, and it's been Tesira trained. So the machine learning process has fed it lots and lots of signals that are relevant and common to a typical Tesira system with different microphone types, different room geometries, that kind of thing. And by doing so, we've managed to provide an algorithm that reduces noise in a meaningful way and reverb, but while retaining speech quality in a much better way. And as a result, we've also improved the double talk performance in 4.7 onwards. And double talk, if you don't know, is the most stressful situation for a DSP system. It's where the near end and the far end are talking at the same time. The near end microphones are open, and we're using AEC to remove the far end echo, and we're also trying to deal with local noise as well. And this new algorithm deals with that much better. The update also applies to launch. Even if you've got a system that's running 4.5 and using the AI process, the new algorithm does benefit this as well. So all you need to do to update, and I do recommend updating in systems where you can, just apply the latest firmware to your launch system. It is necessary to run launch again. The changes in the intrinsic base configuration of the device. So updating the firmware on its own is not enough. You need to rerun launch, rerun the configuration, and you'll get the benefits of the new algorithm. And in launch, it's a couple of sliders. It's very straightforward to use it or not. So this is the default configuration from a factory fresh device, which has just been launched. So AI noise reduction is enabled by default. You can disable AI noise reduction as well. This actually disables the noise reduction process and the dereverb process as well. And when you do so with this toggle, you end up with standard Tesira SCX noise reduction. So the one that you've always known, which is very good at removing steady state noise, such as HVAC, that kind of thing. I wanted to point this one out because it's not the most intuitive way of doing it, but if you turn AI noise reduction on, you also have the option to bypass it. And when you do this, you actually bypass all noise reduction through the launch configuration. This is not actually intended to be deployed. It's for demo purposes mainly, so you can toggle on and off what the system is doing, demonstrate it to the customer so they can hear the benefits. And it's reflected in the report card when you have it enabled. So you'll see the noise reduction applied is enhanced mode, meaning AI is on. In the advanced report card, you'll also still get discrete measurements for the noise at the microphones as well. And the big one is user configuration. So we've added the noise process block to a custom configuration system. So it's in Tesira software now. And there are many reasons for this. The first one is the obvious one. Some conference rooms, and conferencing is the use case that you're mostly going to find a good reason to apply this. But some conference rooms have functionality which isn't covered in the launch configuration, and that's fair enough. That was always expected. A typical example would be a typical conference room with far end microphones where you want to add a handheld presenter mic or something like that. Previously, you could do that, no problem, if you were using a Forte X system, but because you didn't have the noise reduction block in the software, you would lose that capability from the processor. And indeed, it now supports use cases beyond conferencing, so we haven't imparted any line rules on where you can place the block, so you can place it pretty much anywhere you like in the layout. There are good and bad places that you can put it, and we'll talk about that later on. But you can put it in front of a path that leads to the loudspeakers. So public address, you might be paging to a warehouse and you want to use the processing that is now supported. So we'll move on to look at the technology in a little bit more detail. And it's actually very simplistic in what you get in the software. It's doing something very complicated in the background. So it's a single channel block. There is a few reasons why it's a single channel block. Firstly is the processing is very capable, so it can act on a mix of microphones and provide the desired reductions in noise and reverb. The other reason is it is very much resource based. So if we would love to give you 24 channels of discrete noise reduction, but actually it's a very processing intensive algorithm, of course. So if we did that, then there would be less resource for the DSP to do the other things that you need it to do. But adding it to a layout is quite simple, and it offers 3 discrete levels of processing intensity for each process, so for noise and dereverb. You can bypass either discretely with the off button, and there's a master bypass in the block, which is good for tuning, A/B testing, and demoing the processing. And it's found in the dynamic object drop-down menu like any other block. Select it and drop it into the layout. But what can I actually expect it to do? And we'll start with noise reduction. And with our standard noise reduction process that we've always had, it was much easier to quantify because it was very much designed to work on relatively static noise sources like air handlers, that kind of thing. And we could give you a rough estimation of the kind of dB reduction that you'd expect, but it's much more difficult with the AI process. The reason being is that it acts on many different noise sources that cover a broad spectrum. They can be very different impulses at different levels of intensity. So to give you numbers is very difficult, but I've got a little example here which I've taken. So this is actually our boardroom system at Biamp UK with the door open. So anyone who hasn't been here, it's a open plan office. So there's an atrium as well. So there's 2 floors, which kind of acoustically meet this office. So we've got background music, we've got an open office with multiple people typing, working away. We've got a kitchen area, we've got sound masking. And I just let it do what it was doing, and you'll see that with the low setting, it's got what 26 dB roughly of reduction. And low will provide a reduction to not only static but dynamic noise sources, but it'll also preserve the natural tone of speech, which is quite important. You can expect this setting to allow some noise through. It's not going to be total silence. It depends on the intensity of what's being heard at the microphone. If you move it up to medium, it's a good middle ground. So you're going to have a very drastic reduction in ambient noise. So typical ambient noise will pretty much be gone. Dynamic sources such as keyboard tapping, people eating crisps for some reason, will be severely reduced. But again, you might expect some of that to be passed to the output. The good thing about that, though, is the actual speech quality is still well preserved. Whenever we're doing a processing like this, which is really altering the waveform, there are going to be some side effects, some artifacts, and this is a good balance. Now, high is kind of the impressive one. It will remove most static and transient background noise, even at high intensity. So you can provide a very clean signal to the output with this. It works very well. It does preserve speech as best as we think is possible. It's not a catch-all in every situation. We can't guarantee that some noise won't make it through, but it's incredibly effective at making a very clean line with which to pass the speech on. Now, dereverberation, as it's often called, we're calling it deverberation. It is much more difficult, and I've got a little a comment here which you may enjoy from an anonymous Biamp applications engineer. It could be anyone, and it has been everyone, but there's no means by which one can reduce reverberation in DSP processing, and that has been true for most of time and most of my career. And here we are in 2023. Now, deverberation reduces the effect of room reflections on speech intelligibility. Now, the problem with reverb in something like a conference room or a training room, the kind of systems that we would tend to deploy Tesira in, is the reflections of the local voice around the room merge and smear speech components. So, phrases, consonants and vowel sounds will begin to smear and the intelligibility goes down. So the deverb process uses a deconvolution algorithm, which is acting on the source input in real time. And what that means is it's trained to separate direct from reflected speech and deliver a more dry signal to the output. So it's a very, very intensive process, but it can really help clean up the signal and improve that direct sound. And this is basically impossible to put any numbers on. So I'll go with a functional description, really. So low is very useful for reducing reverb and retaining the speech characteristics. Medium offers a pretty good balance between reverb reduction and natural tone. Again, you can expect a fairly high level of reverb reduction, making the source audio feel much closer, a bit more direct, less smeared, with a good clear speech intelligibility. Now, high, and this applies to all of them, but high is a good example to give you. We can significantly reduce the ambience in systems that have a high signal to noise ratio, and that's a system signal to noise ratio. So the system ratio is a combination of the actual reverb time, the RT60 in the space, and the system design, so the placement between the microphone and the participant. So when you have a really good signal to noise ratio, you can make a very dry signal, with podcast kind of effect. If you have a system that has a poor signal to noise ratio, so maybe a high reverb time or an average reverb time, but the mics are much farther away from the participant, reverb will still be reduced. But as the signal to noise ratio of the system decreases, the speech artifacts will increase. And what you'll hear that as is like a modulation on the signal. The naturalness is kind of removed slightly, and there is, as the processing is working, it will take some of the dynamics out of speech, and speech is of course a very dynamic input signal. The best thing to do is hear it. Please come and visit us if you're attending ISE next year. We're at 3D 100, which I believe is the same spot as last year. We're going to have a demonstration system for you there with headphones. The sources you'll be able to choose as well, so you can listen to lots of different acoustic environments with reverb and noise in various quantities. Those will be pre-recorded, but the processing won't be pre-recorded. It will be running through a real system with a Tesira 40X, and you'll be able to choose different parameters and have a listen to it yourself. So yeah, we'd love to welcome you there and come and chat to you about this and all the other things that we've got going on. Grab a coffee or a beer. So how do we actually use this? The first place to start, as always, is with design, and I'll go back to one of my comments again, but modify it. So there's no means by which one can reduce reverberation and dynamic noise in DSP processing. And cut to 2023, the same is true when you consider that there must be some compromises. And I make no apologies for stealing this slide out of the parlay optimization training. So anyone who's attended that before, I apologize. But it's a good way to illustrate the concept. So we're looking at background noise here, but the concept applies to reverb as well. But this is a much easier way to understand it. So we've got our background noise and we've got our talker signal. The inverse square law dictates that for every doubling of distance between the talker and the listener, the microphone, we lose 6 dB of source signal. And when you look at the difference between the background noise and the source signal measured at the microphone, you get the signal to noise ratio. So just a standard example, take away the difference and you get a signal to noise ratio. Now, reverb is more difficult to quantify and illustrate in this diagram because it perceived to scale to the actual volume of the input signal. But this concept applies as it always has done. And the truth remains the same. The higher the signal to noise ratio, the clearer the speech will be. And you'll notice if you look at the way we design parlay systems, and I should point out now that I'm going to talk about parlay systems a lot in this training, but AI noise reduction is not just for our microphones. You can use this on any microphone that you like. But you'll see in the table, as the noise floor and the reverb time increase, the maximum mic to talker distance must decrease to preserve a good signal to noise ratio. And a good signal to noise ratio equals good results. How much louder is the talker versus the background noise or the thing that we don't want to hear? And the direct to reverberant ratio is as important as ever. And if we use the tools and the concepts that we've learned to design systems as we always have, when you do this properly, you'll end up with a system that's going to perform well and to the customer's expectations. And then you can use this processing to improve and make an extraordinary experience. It's important to note that it cannot overcome poor system design. You can clean up a mic signal, particularly with reverberation. You can reduce reverberation, but there's no such thing as a free lunch. So when a system is designed properly from the outset, we can actually just make it extraordinary. We can't fix acoustic design problems in DSP. What do you need to actually do this? Well, You really do need one of these. You can only use AI noise reduction when you have a Tesira Forte-X processor. It is, of course, our kind of flagship product, I guess. But the hardware that it's designed around is why you need one. And this is because the AI processing runs on a dedicated core inside the host CPU of the device. It's the same for any Model X, 400, 800, 1600. What that means is there is a one-to-one ratio between Forte-X DSPs and AI noise reduction blocks. And if you think that's going to be limiting, there is some limitation, and that's simply because of the resource of the device. But the positive is the assigned core means that deploying the block has practically zero impact on your regular DSP resource. This is processed elsewhere to the DSP that you normally use when programming the Tesira system. And if you look at a really basic example here of input to output, you'll see on the left-hand side that we've got 0.9% of the DSP usage. And indeed, adding the AI noise reduction block doesn't change that at all because it's being hosted elsewhere. And while we're talking about hardware, there's an example that I'd like to give, because we've had a few calls about this already. And if you look at this example system, so this is your traditional a small divisible room, so it can go into two or in one, and we've got 4 microphones, and we've got the USB output of the Tesira Forte-X running one room when they're separate, and we've got an XUBT which runs the other one when they're separate. We've got a requirement for 4 AEC channels and 1, 2, 3 AVB PoE ports. So actually, you have enough hardware to do this with a single Tesira Forte-X 400 until you add the noise reduction block. Because it's a one-to-one ratio, 1 block per DSP, if you were to build this system and add those 2 noise reduction blocks, you're going to be seeing an extra Forte-X processor added to your equipment table. So yeah, important to remember this now. It's not nice to find this out when you're on site. So it being an intensive process, there is a lot of data churning going on. There is some latency that's going to be imparted when using this block. So here's a baseline of analog input to analog output is less than a millisecond path delay through the processor. Now, if we add the AI noise reduction block, we've added 52 milliseconds of processing time. So the time it takes from that input signal to get to whichever output it is we want it to get to is at 52. That might seem like a lot, and in some applications it is a lot, but for a far-end conferencing system, which this will mostly be deployed in, it's no problem at all. So the local user won't be hearing that, and the far end will have no idea that this extra 50 milliseconds of latency is there. But because this is an important concept to consider, I do have an example for you, and hopefully everyone can now see Tesira software. Yeah. So consider this system. We have on the left-hand side parlay microphones. They're going to the UC system, or BYOD, could be anything. It's going to the USB output. But we've also got some handheld mics, and these are going to be used for 2 purposes. So they will be sent to the far end. If you're talking on a handheld, the far end still want to be able to hear you, but we need local reinforcement into this system. So these handheld mics are also being routed to the local amplifier so that the audience can hear themselves. Now, when we considered the 50 milliseconds of delay this is going to add, that could be problematic. And Tesira has a concept which we won't go into too much detail, but it's called delay equalization. Now, it's important that in certain applications, the inputs are time aligned at the output to stop problems with phase and that kind of thing. Now, this path is going to take a while to get through the DSP because of all the processing we've got in line. AEC processing is about 14 milliseconds as well, and then any filters, that kind of thing. If we send the handheld mics with the same, and I should mention that delay EQ is managed automatically in Tesira. So if you just leave it to do its own thing, it's going to align everything for you. And a lot of the time that's perfect. But in a situation like this, you're going to want to amend that, because we want these handheld mics to get to the far end as well. We actually don't care about the processing time to get there to the far end, because we won't notice it and the far end won't notice it. But when we're getting them to the local loudspeakers, if we have 50 odd milliseconds, 70 milliseconds of latency there, the person that's going to be speaking in the room is going to hear that delay. And when you hear a delay of yourself coming back, it's off-putting. So we can do something about this. So if you look over to the right-hand side of the screen, so we've got delay EQ group default AC for the Parlay microphones, and the handheld microphones have been placed manually by me into a different delay EQ group. And if I now run the compilation again, you see I've now got two discrete delay paths through the processor. So default AEC inputs can take 76 milliseconds to get to the output. That's fine. And default inputs, our handheld mics, will only take 3.3 milliseconds. So the local presenter is not going to hear themselves as a discrete echo or with any delay, and it won't be off-putting for what they're doing. Tesira also supports decentralized processing. Now, you do need a Forte-X to run the AI noise block, but you can place it anywhere in a layout. And if you've got a system that has multiple devices, this example here is a server I/O. So the path is wholly hosted in the server I/O with some processing here, and it outputs from the server I/O as well. We can still use the AI noise block, and the beauty of implicit AVB makes that autonomous for us. The blue line will pass the audio path into the Forte-X for processing and back to the server I/O. So it's absolutely acceptable to do this. And just a quick example of what that means is you'll see that the delay EQ through this is essentially the time for the AI noise processor and 2 AVP hops. But to strip it back, this is going to be, I'd say, 80% of the places that it's deployed. Not necessarily with Parlay microphones, but oftentimes it will be. And where do you put it? Well, after the mixdown, we haven't added any line rules. That means we haven't made Tesira software block where you can place it in the layout, apart from the obvious ones. So you can't put it in front of AEC, which is true for any block of this type. It needs to go post AEC. If you've got multiple microphones, you've only got one channel, so it needs to go from the mix. This is a really minor point, but something I like to point out. Where do you mute your microphones to the far end? And this applies not only to AI, but also to AEC. You could mute them at the input, but the problem therein is actually, while they're muted, the AEC processing is not getting any signal with which to act on and converge on, and the AI isn't either. AI takes a very, very short amount of time to converge and start removing unwanted noise. But if the mic is muted, it's getting nothing. And when you unmute it, all of a sudden it has to figure everything out. So best practice would dictate that you mute it after the block. And this is actually, this makes sense anyway, because if you're connected to a UC system that supports mute sync, this output block is the one that's going to track to that anyway. As I mentioned, you can place it wherever you want, but you could find yourself unstuck and confused if you don't consider it carefully. Now, here the mics are routed through the AI noise reduction. That's great, that's what we want. But we've also got a program input on the analog ins. We don't know what this content could be. It could be anything. It might be music, and you may want to send it to the far end You know, you might be discussing a new advert or something with your colleagues remotely. If you route it through the AI noise reduction, it doesn't know. It's going to act on that as well, and it's just going to try and separate speech from anything else is there. So if you route music, it's going to do its best to remove all of the instrumentation and preserve the speech with limited results. The fix is easy. There's loads of ways you could fix this actually, but here is an obvious one. You just route the microphone signal separately from the program material to the output. We also support external control in the form of presets within the Tesira system. So here's an example. Let's say this is a boardroom system at a scientific research lab. During regular meetings, they use their ceiling microphones. It gives them freedom of movement. They don't have to think about the microphones at all. They can get up and walk around. They can go to whiteboards, that kind of thing. It's much more informal in this way. Now, perhaps they're discussing a new scientific breakthrough and they want to record the discussion and they want to broadcast it to colleagues elsewhere. They may choose to use their gooseneck microphones because it gives them individual mute. It's going to give them a really direct pickup for recording purposes. Now, when they're also using the AI to make sure that they've got a really nice clean signal. When using the ceiling mics, they've obviously got a much different acoustic path than a gooseneck microphone would, simply because of the placement. So you might tune the noise reduction for the gooseneck mics and be happy with it, but then when you switch over to the ceiling microphones, it may not be achieving the desired result. So you can add the noise reduction block to a preset. You can control any of the parameters discretely as you wish. Right, we'll have a quick look at a sort of typical tuning process. So I've got a little system here. This is a live system which is working. We've got 3 table microphones, and I'll start with something that's probably not that obvious, but start by bypassing the AI noise reduction. Attend to the other things first. And then the next step would be to bypass standard noise reduction as well. It's probably a good point to mention is it's perfectly acceptable to use both processes in the same file. Because the noise reduction is great on steady state things like air handlers, that kind of stuff. Feel free to use that to clean the signal up before it even reaches the AI or any other processing that you've got. I would recommend not using high. If you're going to use both together, try and limit the intensity of the processing that you're using in both of them. So if you're using 2, I would say avoid using high in either one of them, because you'll end up really affecting the speech signal in a way that's less than desirable. And then you may want to move on to this, and this is optional. So a Q output on the right hand side here, you could make a cable, and I've got one in my bag, connect some headphones to an analog output so you can listen to the processing directly. This is optional because the benefit is it gives you the true picture of your microphone mix, so it's great at making decisions that way. If you can't do it, it's actually not the end of the world, because let's say in this system we're connecting it to a MTR or a Zoom room system. Whatever that downstream system is doing, so how the codec performs, any additional processing with AGC and noise reduction it has, we need to take into consideration anyway. So the next step after that is to actually get yourself in a test call. And then move over to the left-hand side and tailor your microphone coverage first. I'm using Parlay as an example, but it's true for any microphone. So, the directionality of the mic, it could be in the design stage, what polar patterns are we using, or if you're using another beam steering type of microphone, you want to tailor the coverage first. If I'm speaking over here, and actually this microphone may be up against the wall, let's tailor the coverage and turn off the bits that we don't want to actually use anyway. And I'd suggest doing that at the outset so that you're only covering the areas you want to. And then you'd want to move on to tuning the mics. So any dynamics or EQ would be the next stage. Now, during this, you might be listening to individual mics, and I'd recommend doing that. But once you've got your mic mix happy, so you're happy with the tonality of the mics, then you can start moving on to what we're actually talking about. And in that case, I would strongly recommend isolating each microphone first. So listen to one in turn, and you can use the auto mixer just to verify that you are indeed listening to that. If you don't do this, sure, you could go and speak directly to a mic, but you might be opening other gates, so you're not getting a full picture of how each mic sounds as you're applying the processing. So this is a really good way to do it. And once you're there, if you want to use standard noise reduction, and I do recommend experimenting with it. If you've just got a bit of really kind of steady background noise, feel free to use it in one of the lower settings. And then you can move on to the AI block. And I'd start by doing each in turn. So turn off deverberation and start with noise. Now, what you want to do is test it with speech and various different noise stimuli. So, try the keyboard tapping, the paper rustling, that kind of thing, and test it and use your ears to find the setting that achieves the best result. Always use the lowest setting that achieves the result that you want, because if you're processing more than you need to, then you're just impacting the signal and changing things that you don't want to actually change. And do the same for deverberation, and obviously moving through each mic in turn. And when you're happy with each microphone, and bearing in mind there'll be different acoustic paths between microphones, different geometries depending on the mic type of the room, and the levels that they're receiving from talkers, as well as background noise and the effect of reverb. So find a balance for the level of processing that you need to use. And then once you've done that, get the whole system open and do a regular test call. So treat it as if you were doing you were the user. Move around the room, have multiple participants, keep doing different noise stimuli, different levels of speech. The louder someone talks, the more of the ambience, the reverb of the room, which is going to be picked up by the microphones. All right, how are we doing for time? Okay. And these are in the handout just as a reminder of what I just said, but test all of the inputs, use a range of noise stimuli, different talker levels, and use the lowest setting that achieves the desired result. Less is more. So you see, just a selection of our partners there. There are obviously more. And another statement, which always used to be true: disable all processing in the downstream device, i.e. the UC codec or whatever it is you're using. Hand off all the AAC processing to the dedicated DSP, which has been manufactured specifically to handle this kind of thing. And once again, that's changed in 2023, or perhaps a little bit before that. Let's consider a typical user. Say this is a BYOD or a BYOM room. Someone turns up with their laptop and they're using Teams or whatever it is. They have control over the noise suppression. The DSP doesn't have control. Although we have certified endpoints, the DSP can't get in here and change your settings. And I actually was having a call with a customer the other day, and they said, your noise is really bad. And it turned out I'd disabled noise suppression in Teams to do some testing and forgot to turn it back on. This is the kind of thing that you're going to experience. Does a user know or care about this? And should a user have to know or care about this when they come and connect to a Biamp conference system? Probably not. And the same is true in Zoom or any of the other applications. I don't think it's right that we expect and mandate that users should start reconfiguring their personal systems just to use a particular conference room. And for that reason, we've designed the AI to work well when connected to a variety of different UC recording and telephony solutions. And best practice still dictates that multiple processing algorithms working in conjunction is less than ideal. And it does still hold true to an extent, but as we just discussed, this might be unavoidable. We have tested extensively internally to make sure that our algorithm is playing nicely as best as possible with any others. And the reason being is nowadays the AI processing in certain UC vendors, some of them are very good and they're also very useful. In some tests in particular rooms, I found a really nice. The best sound was actually using maybe medium noise reduction in the Tesira and allowing the UC system to do its own processing. If you deliver a good signal to the UC system, it's got much less junk that it needs to act on, so its processing is working much less hard. I know a lot of it is cloud-based now, and if you deliver a good signal, generally you're getting good signal out. What to do? Well, trust your ears and your judgment. If this is going to be out of your control, make the best compromise for the best sound for most users. So yeah, you choose the level that suits the system and the application. And when you're connecting to a UC system, so the Lovo system, certification has been achieved using standard noise reduction. So we were certified for Tesira and Deverberation a couple of years ago now. That we were certified before our AI noise reduction and Microsoft Teams AI noise reduction was even released. So it's useful to point out that if you want to deliver a certified audio system that's rubber stamped, you actually need to use standard noise reduction when using a Tesira or Deverberation. But that's not the whole picture. So what is the actual purpose of being certified? And it's so that a vendor like Biamp or anyone can reliably deliver a solution that meets the expectations of the user and the UC provider. If somebody buys a Zoom room system, they expect that system to function in a particular way. And when you start connecting third-party devices, that vendor, such as Zoom or Teams or whoever, needs to make sure that they're going to guarantee a good experience for their users. So actually, you have pretty good options available to you. If you need to deliver a system that is absolutely rubber stamped and certified, do that. You can disable AI, no problem, use the standard one. And if the user's happy and you're happy, then great. If you found that the Biamp AI is preferable, having it enabled gave you the best sound for that particular design in that room, then it's up to the customer to decide what they want to do. There's actually minimal risk here because if you've achieved something that's even better than they were expected or better than they bought into, then you've won. If they really do need to meet this is certified in this way, then it's just a toggle switch, and you're back to having the checkbox ticked. One thing I will say is handoff is something that is often discussed, and what that means is when you connect a certified endpoint like a Biamp Tesira DSP to a UC system, if you've met certification, traditionally we've always expected that the AEC would be disabled and noise reduction would be disabled in the UC system. That's a bit of a moving target nowadays, and anyone who's used an MTR, for example, will know that even when you've got a certified endpoint, the noise reduction process is enabled for every call, and you can disable it manually, but it will be re-enabled for the next call. You can go into the back end of the system and disable that. It's just a small modification to an XML file if you want to permanently disable it. But it just goes to show that things have changed, and we have to work with what we're connecting to. And that is it. And once again, thank you. We're going to close the call now. Any additional questions, do point them to support@biamp.com. Thanks again, and enjoy the rest of your day.